Hi all, welcome back to another lecture of DBMS, and in this lecture we will learn about Armstrong axioms, in which we will learn about 7 different types of inference rule which we were talking about in last lecture: reflexibility, augmentation, transitivity, self-determination, decomposition, union and composition. So stay tuned for the video, and this video is going to be very much interesting and important. So let's begin with the first topic, which is Armstrong's axioms. So what are Armstrong axioms? These are a set of fundamental rules, basically inference rules, for inferring all the fundamental dependencies that hold a relationship in database. The axioms provide a framework for reasoning out functional dependencies and play a crucial role in database normalization process. So basically these are the inference rules, nothing but inference rules. Okay, so with which we take help and create more necessary information. If we are not able to find out the relationship with the provided functional dependency, then with this help we can find out more functional dependencies out of those to make the information and relationship more clear in the relational database, right? So based on primary rule and secondary rule, we have here 6 different types of rules, basically axioms. So with the primary rule we have reflexive, augmentation and transitive, and using the secondary rule we have decomposition, union and pseudo transitive rule. So let's learn one by one. First is reflexivity. So reflexivity says, it is one of the basic Armstrong axioms, which states that if y is a subset of x, then x determines y. In other words, any set of attribute can functionally determine any subset of itself. So it says basically, let's suppose train ID and train name are the subsets, right? And they together says determines train. So this is the example of reflexivity, which says that train ID and train name includes train name. So it can be trivially determine itself. So it is independent, right? So this is a trivial functional dependency, as a subset of attribute is always determined by the larger set of contents. So as you can see, the train name is already there in the left part, right? So it is a subset, right? The determinant, which we are finding out, is already a subset of this. So this is called reflexivity. So here in this case, we can say train ID can determine train name instead of including train name in the left part. This is what reflexivity means. Coming to augmentation, it says that it allows add attributes to both the sides of a functional dependency. So let's suppose we have some x determines y, then we can add z both sides. So if we are say employee ID determines employee name, right? So both sides we can add age. That will not impact the functional dependency. This rule suggests that if one of the set of attribute determine other, then adding the same attribute to both sides of functional dependency does not change the relationship. So here let's suppose we have train ID and train name. So we are saying train ID can determine train name. So adding the passenger to train ID. So along with passenger, now train ID can determine train name and passenger. This means if we know the train ID and passenger, we can determine the train name and the passenger without changing the logic. Anyhow, it does not mean anything, but in some cases, if we want to reconfirm the name of the passenger with the train ID, then we can find that with the help of this augmentation rule, which says that if you will add that same attribute to both the sides, determinant and dependent, then that is not going to change the logic, and that is what augmentation means. Coming to transitivity, it says if x is determinant of y, so if x defines y and y defines z, so with the transitivity rule, we can say that x also defines z. How? Basically, it reflects a cascading logic where one dependency leads to other. So the first attribute can determine the first outcome by going through an intermediary set. So let's suppose if we say that train ID defines train name, so x determines y. Okay. Now train name determines source, so y determines z. So we can say with the help of transitivity rule that x also determines z. Why we are doing so? This with all these rules, okay, when we are if we are confused in the functional dependency to find out the relationship, so with this all rules we can break down the relationships to understand more clearly, either in normalization or denormalization. These rules help to understand the relationship in both the ways. Okay, so basically that is all the transitivity means. If x determines y and y determines z, then x can also determine z, right? So this is what, with the help of this train ID example, if train ID determines name and name determines source, then train ID can directly determine source as well without the help, without intermediate like inference of train name in between. So that was transitivity. Now next is self-determination. So it says that any set of attribute can always determine itself. Obviously, A determine A, train ID determines train ID. And this is true for every attribute. So this is a trivial rule for functional dependency, but trivial means it does not give any new information, but it serves as a functional dependency concept in database theory. It also comes under the functional dependency. So passenger defining passenger, it is a self-determination. This means that attribute passenger determines itself, and this is obvious and trivial functional dependency, as we know that it is always true and that is not going to add any new information. That is why it's a trivial dependency. And it is true for each and every attribute, either whether they are primary or whether they are non-primary. Next is decomposition. So breaking down a functional dependency into smaller one for more specific dependency. Like if we are saying X can determine Y and Z, right? So basically we can say X can define Y and X can define Z also. This is what dependency means. When we are confused in these two attributes, then we can decompose it, basically break down to understand more clearly. So if we can say that train ID defines passenger and date together, it means that train ID can define passenger and train ID can define date as well. This shows that knowing the train ID can determine the passenger and date independently. Okay, so here if we have train ID, so with the train ID itself, we can find out the passenger name from here with the help of train ID here in this booking table. We can say the passenger name, and similarly train ID itself can say that what is the date it has been booked for. There is no need to combinedly defining both the attributes with the train ID. That is what decomposition means. Next is union. As the name itself says, if X determines Y, union is totally opposite to decomposition, right? Where we were saying that if X determines Y, Z, we were saying X determines Y, X determines Z, right? This was decomposition. It is totally opposite in union case. If we say X determines Y and X determines Z, we can say X determines Y, Z together. So then we can combine them, and this is essential for the opposite decomposition, where multiple dependencies are merged into a single one. Okay, so depending upon the needs, we go for these inference rules to understand, basically to understand the functional dependencies and the relationship between the attributes more clearly. So from the booking table, we know that train ID defines passenger, okay, this one, and train ID defines date, okay. Now we can say that union of this, it's totally opposite to decomposition, that train ID can define passenger along with the date together. Okay, this means that knowing the train ID will let us know both the passengers together, and in decomposition it was independently. Okay, so both are same, but only like one is breaking down table and one is integrating or union, making them union back. Now last is composition. So composition means it allows us to apply functions across multiple relations. So if we have X determines Y and we have Z determines W, so we have total different, all four attributes are different, but it says composition that X multiplied by Z means left side, together they can define right side combination. So how? Let's suppose in the IRCTC database we have train table and we have booking table. So train ID can say train ID determines train name, okay, first, and booking ID determines passenger, okay. This we have, right? So it says if we have the combination of train ID and booking ID, means 101 and 201, we can say that train name will be Rajdhani and passenger will be Raj, right? So that is what combination means. If we have totally two independent functional dependencies, then the combination of determinant and the combination of determinant can define the combination of dependent, right? This means that if we know the both train ID and booking ID, we can determine both the train name and passenger's name. This is helpful in case when information is spread across multiple tables. So if we have here we have two tables, but if we have multiple tables, then this rule help us to find the information and related to by combining functional dependencies. So these were the few Armstrong axioms rules which help us to find new functional dependencies out of the already formed functional dependencies to understand the relationship between the tables more accurately and help us to define or break down the tables to form the normalization or the opposite denormalization also. So that was all about the whole different rules. I hope you learned, and that these were very much important when in case of like the interview asks you to normalize some table with the help of some functional dependencies. Then knowing these rules are really gonna help you to solve that problem in the interview. So I hope you will re-revise it. If you have not understood any of the topic, then I will request you to revisit the video again to learn that with more accuracy. And yeah, that was all about the whole video. Let's meet in another lecture. Till then, keep learning, take care of yourself and your family too.